net external force being the rate of change of momentum of the system. So when the net external force on a system becomes zero, then we apply what is called momentum conservation. So let us look at some examples of application of that today. Okay. And of course, before that, we have seen the concepts of position of center of mass, etc. earlier. So calculation of position of center of mass is another aspect of this chapter. So we will look at some examples of questions related to position of center of mass also. In fact, we'll begin with a couple of questions like that today. Okay. So this is system of particles. Session number 6. So we will start with this example today now. Okay, we have a disk like this, okay, and from that disk, we have sliced out. Okay, we have sliced out a portion of it, like we've cut out a cavity in the disk. So I'll just make the diagram a little more clear first. So a round hole or cavity has been cut out from the disk. In such a way that the portion we have remaining is this one. So if this is one symmetry axis or diameter of the disk, and this is another diameter of the disk, so you can see that this is a thin uniform disk, okay, with center at O, radius capital R, and in the XY plane, with a round hole such that OP equals to the diameter of the hole. OP is equal to R, the radius of the original disk. Okay. So we have to find the position of the center of mass of this disk with cavity. It's not a full disk, it is a disk which has a cavity. Okay. So this structure, you can say, we have to find the position of its center of mass. Okay. So just note down the question and try to visualize how we'll solve it. I'll explain it. I'll tell you what is the concept in this question. So you would have realized here that is there any axis of symmetry you can tell?
So x-axis.
Very good. X-axis is an axis of symmetry. Why? Because OP is the diameter of the hole. Na? So हमने hole ऐसे करके cut किया है that if you see, if you fold that structure about the x-axis, now it will fit exactly. Na? Like the above part is like a mirror image of the lower part, right? So x-axis is an axis of symmetry. So that is one thing. So then we can say, okay, the center of mass is lying somewhere on the x-axis. Now, where you estimate the center of mass should be on the x-axis? Should it be on a negative x-coordinate or a positive x-coordinate? Anybody tell me? Like,
So negative.
Negative part में होना चाहिए ना, because हमने hole जहाँ cut किया है, वहाँ mass कम हो गया है. So the mass is concentrated more on the negative side on the x-axis compared to the positive side, right? So this concept must be clear to all of you. So I can now say that, okay, the center of mass must be somewhere over here. Now the thing is how we will find the exact position where the center of mass is. Okay. So listen to me carefully. I'll explain. This is a very important concept we'll learn through this question. And that concept is called superposition. Okay. Now superposition is an important concept in all of physics, not just these type of questions. We use superposition whenever we want a situation where we can add two events and get some resultant event. Okay, so let me explain. So, but before that, let's observe these two things. That because, okay, the cavity is a round hole, a perfectly round hole. Okay, with,
Sir,
yeah, tell me it.
sir, we have to find the center of mass of remaining part. Yeah, that.
Yeah, the remaining part. ना जो अपने पास जो shaded portion है ना, उसका center of mass निकालना है, right? So it's like you have a cardboard disc, उसमें से मैंने ये hole cut कर दिया है. So now I have this structure left, which is a disc with cavity. So its center of mass I want to find out, right?
Yes, sir.
Okay, so because the cavity is a perfectly round hole with the x-axis as its diameter.
Sir, will it be minus r/3?
Minus r/3. Okay, let's just check out just a moment. What is the method you applied? You tell. Okay.
Sir, its thickness is same now. So,
Thickness as in?
sir, means density is same now of this material.
The whole thing's density is same. That's correct. Okay. Or you can say mass per unit area, you know, because it's a surface distribution. So sigma is same for the whole thing. Okay. But how you can directly say it's r/3? There must be some logic you are using. Tell me. Okay, x-axis is an axis of symmetry, first of all. Okay, I'll come back to your point, beta. Okay. So axis of symmetry, that means the first thing I can say over here, that therefore the center of mass of the given structure, which is basically the disk of radius r with the cavity, not the entire disk, okay, disk with cavity, which is a round cavity of radius r/2. Okay, so because of this thing, the center of mass of the given structure is on the x-axis. Okay. So in fact, I know it will be somewhere over here. Let's see. So I just don't know its coordinate. So let C has an x coordinate of x cm by coordinate of 0. You want to find the position of the center of mass. Okay. And xcm will obviously be a negative quantity. Okay. Okay. Now what we'll do here is we'll use the principle of superposition. Okay. So this is what I was telling you about. Okay. Principle of superposition में हम क्या करेंगे? The term superposition just means addition of two events. Okay. So superposition just means addition, okay, or you can say superimposing, that is putting one on top of the other. So superimposition of any two events such that the resultant event is something well known. Okay, so how we'll use the principle of superposition? So in like this is a general principle. We can apply it in this chapter. We can apply it in current electricity. We can apply it in rotational mechanics. We can apply it in number of places later also. We'll see. So general मतलब क्या होता है? Principle of superposition, that we can add two events or superimpose two events. Okay, such that we get some resultant event which is a well-known event for us, okay, which is something easy to plot. So here what is the two events that we can add? One is that we have this mass which is given to us, which is looking like this on top. The other is that now imagine जो cavity मैंने cut किया है, it is a disc of radius r/2. It's a smaller disc. So if I place that disc back on over here from where I've cut it out, so I'm superimposing the given mass, which is the blue shaded portion, with the mass which I have cut out from here. So when I superimpose these two things, what is the resultant that I get? The resultant is the full disk.
Yes, sir.
So the resultant is a very well-known event. The full disk, I know its center of mass will be at O. So can I make use of that concept? कि मैंने ये वाला जो mass है, suppose this mass is m1. Okay, so this is the mass of the full disk minus the cavity which I have removed. Okay, so suppose I superimpose this mass m1 with a round hole like this, which I have actually removed, and I place that round disk of radius r/2 back over here. So let's say my second event is this mass now. Okay, so this is mass m2, which is like a disk of r/2 radius, which was cut out. So if I superimpose this smaller disk back into the cavity, then the resultant will be a full disk, and that is something very easy for me to understand because that's fully symmetrical. So uska both the x and y axis are axis of symmetry, or any diameter is an axis of symmetry. So for a full disk, I know that all these axes are axis of symmetry. So they all intersect at the geometrical center. So that is the center of mass. Okay, whereas I also know that this one center of mass is here. I know this one center of mass is here. So if I superimpose these two things, I know the resultant center of mass should be where? It should be at the origin. So here what we will use is, we will superimpose the given body, which is the disk with the cavity or disk with a hole, with a smaller disk of radius r/2 or diameter OP that I had drawn earlier. Okay, so superimpose the given body with a smaller disk, okay, to fill the cavity exactly. Okay. So the resultant of this superposition, this will result in a complete disk. Okay, with its center of mass at the origin. So can I now use this concept to find the center of mass of the given structure, which was the disk with the hole? Okay, so hope this concept is clear to all of you. Okay, just make a note of this part over here. Then we'll discuss how we'll do this mathematically exactly.
Sir.
Yes, beta.
So, sir, after copying this, we are going to show that upper part as well.
Okay, you want to copy the upper part, no? Okay, first, okay.
So that question also.
Okay, question also, okay. You finish this part now?
Yes, sir.
I mean, you can just make the rough diagram because I'll send you the notes anyway. Okay, so now what we are doing here is, this is, let M1 is the mass of the disk with hole. Okay, and let M2 is the mass of the hole, or is the mass of the portion which was cut out, and that is nothing but a disk of radius r/2. Now next we are going to use superposition. We are going to place this back over here and see the combination of these two masses when placed on top of each other, or when placed in combination like that, that the whole is refilled by that smaller disk. That combination will give us a center of mass over here. Okay. Now I will actually denote this as C1 because it is the center of mass of this portion of mass M1. Okay. So this has this particular feature because the cavity is a round hole with the x-axis as the diameter. Center of mass of the given structure, which is basically of mass M1, is on the x-axis. It is on the x-axis. So C1 the position of center of mass of M1 mass.
Done, sir.
Done, no? Okay. So you can just note down the general idea of principle of superposition, or just make sure you understand the meaning of the statement here. Okay. And then we will see how we will apply this next. Okay. Okay, so now,
Sir,
yes, tell me.
sir, you would you just show that first statement because actually I'm not seeing the right part.
Okay, just a second. Yeah, this now.
Yeah, sir.
Okay. So now in my diagram here, this disk, I'm placing it back over here. So this is my mass M2, which is a disk of radius r by 2. So I can say that M2 is a mass of some sigma into pi r by 2 whole square. Okay. Whereas M1, which I had originally over here, M1 is the disk with the hole. So the disk with the hole will have a mass of that same sigma, but into the area of the whole disk minus the area of the hole. So it will be sigma into 3 by 4 pi r square. So this is M1 and this is M2. Okay, this part is clear to all of you. M1 and M2 will
Sir,
be
what
like
is
this.
sigma?
Sigma is some uniform mass density, mass per unit area. Sigma is
Okay, sir.
surface mass density of the original disk. From which I have cut out this hole. Okay, so it is basically or in simple terms, it is mass per unit area. Okay. So this is mass per unit area into this one's area. So this one's area is the full disk minus the whole. So the whole actually has 1/4 of the area of the full disk. So it becomes sigma into 3/4 of the full area. And this is sigma into 1/4 of the area. Okay. So now we can see that the mass. So when I place this over here, now remember this is my x-axis. This is my y-axis. So for the cavity part, that is the smaller disk of mass M2, the center of mass is at a position, let's say C2. Now what is the position? It will be exactly r by 2 on the x-axis.
Yes, sir.
Comma 0. Okay. Whereas for the disk with the hole, okay, that is the mass M1. For this one, the center of mass is at some unknown position. So it is at C1, whose x coordinate I don't know. I just know that it's some negative value, but its value I don't know. Okay, so these two are making sense. Okay, but when M1 and M2 are superimposed, okay, we get a full disk. Okay, so this full disk has center of mass at which position? The origin, that is 0, 0. Okay, so that means M1 x1 plus M2 x2 upon M1 plus M2 should be equal to 0, because this one's x coordinate is 0. You're placing this entire mass M1 at its center of mass C1. You're placing this green colored mass M2 at its center of mass, which is at C2. But that combination center of mass should come where? It should come to the origin.
Origin, yes, sir.
So so this step that we have written finally over here, this step is what we call the superposition step. Okay. That we are superimposing the two masses and their center of mass is coming back to the origin. So now in this C, x1 is unknown, x2 is known. So I can replace M1 with sigma into 3 by 4 pi r square. Okay, into x1, which is unknown. This sigma into pi r square by 4, but into x2, which is r by 2. Okay, and the denominator doesn't really matter, so I don't even need to put, but the denominator will become sigma into pi r square, because that's the total mass now. But this should be 0. So more importantly, the relation I'm getting is that 3 by 4 x1 minus, or sorry, plus 1 by 4 into r by 2. So r by 8 should be 0. So x1 is coming as minus r by 6. Okay. So the position of the center of mass of the mass M1, which is the structure that we're looking for, that is a disk with the hole. Okay, that is coming out to be at minus r by 6 comma 0 on the x-axis. So that becomes our final answer. Okay. So I'll just minimize this a little and go through the steps very carefully. Now we will see other examples also as we go along, because this general method of superposition is pretty important in physics. Okay. So center of mass is a good chapter to start understanding the application of this general method.
Sir,
Yeah, beta.
sir, could you just show the upper part working also? Yes, sir. That
This partners.
yes, sir. After that, super.
Okay.
Thank you. Sir, done.
Yeah. Yeah, tell me, beta.
Sir, done.
Done. Okay.
Sir, can I ask you a small question?
Yeah, sure, beta.
Sir, overall, using this,
Yeah.
use only just putting it back to that hole, you are just using that previous formula which you have did, so as to get the center of mass of that.
Wait, Bhargav. Tell me again. Using that, I put that smaller disk back in the hole. That's correct.
So you are just using this m1 x1 plus m2 x2 upon m1 plus
Correct.
m2, using that previous formula.
हाँ,
Because
मतलब देखो, actually what I'm doing ना, actually there's one more hidden step here. What I'm saying is that this blue colored mass you're seeing ना, its mass is m1, that is this much, and its center of mass is somewhere c1 over here, which I don't know. So next step now I can replace that whole blue colored mass with a particle of the same mass m1, but where I should place the particle at x1 comma 0, correct?
yes, sir.
And then I should replace the other one that I have, that is this green colored disk, with the particle of mass m2, which I know, and whose x coordinate also I know at x2 comma 0. This x2 is equal to r by 2. Now these two particle system center of mass should come where? It should come here. It should be at the origin. So that is where this formula comes in now, that m1 x1 plus m2 x2. See, m1 x1 plus m2 x2 divided by m1 plus m2 is the x coordinate of the center of mass of this two body system, na? M1 and m2. So this should be at the origin. So that is how this step is coming now.
Got it, sir.
Okay, na? So that's
Means
the
full
little
body
bit.
का center of mass is at origin.
Yeah. If I put that smaller disk back, then this whole body's center of mass is at origin. So x coordinate of center of mass I should write as 0 because I've taken that origin as my center of mass. Okay. So you will find questions like this in your module exercise. Okay. Today at the end I will give you some assignment questions, like I will give you a list of questions to do both from HC Verma as well as from the module. So you can try them out in the coming week, and we'll be discussing some of those questions in class next time also, apart from the regular questions we discussed. Okay, let's see another example of a somewhat similar example, but actually something simpler. How
Sir,
we
this
can
example
use
was in
superpose.
HC Verma.
Which one? This round hole one, no?
Yes, sir.
Yeah. I mean, this is a standard example. ऐसे दो examples होते हैं actually. One is a disk with a round hole, and then there's another example of a solid sphere with a spherical cavity. So the only difference is in the case of solid sphere with spherical cavity, na, you have to write the mass as density into volume. You understanding, na?
Yes, sir.
So for the full solid sphere, the density into volume becomes rho into 4 by 3 pi r cube. So if you cut out a spherical cavity which has radius of r by 2, its volume actually becomes 1/8, because its volume is proportional to r cube. So the mass that you're cutting out is actually 1/8 the mass of the full sphere. So you can try that example out as homework also later. Okay. Now, as I was saying, a somewhat simpler example next, which you can see. Now, this type of this type of example can also come at JEE mains level kind of thing, because it's somewhat simpler. But so I have 3 square plates made of the same material, of same thickness and same density. Okay, so they should be exact actually. Anyhow, so I have these 3 square plates which I made of and place them like this. So 3 uniform thin square plates. Same material and thickness. Each plate is L by L in dimension. Okay. So if this corner point is P, you have to find the distance of this system's center of mass, that is the 3 plate system center of mass, from the corner P. Okay. So just try this out now.
Sir,
Yes.
sir, between them, is there any gap? or not?
There's no gap. Like that's just I'm showing. Like they're in contact. Okay.
Okay, sir.
So we could have actually made the diagram like this also. Okay, so work this out quickly and tell me. L के terms में answer आएगा. Some factor into L.
The mass is same, no?
They are made of same material, and same thickness. So they will have the same masses each. Okay, now there are 2 or 3 ways of doing this. Okay.
Sir, 1 minute.
Yeah. Okay. Okay, fine. Give it a try. No problem. Yes, anybody got the answer?
Yes, sir.
Yeah.
5Ly.
Jay and
5L by
Harsh, you have sent me the answers. 5L by 6. Okay. Okay, so let me explain a couple of methods by which we can do this. Okay. So one is, see, if I take this point P as my origin, like this is x-axis, this is y-axis, then each square, suppose I replace it with a mass m, okay, then I can take, with respect to the point P, which is at the origin only, I can place this one here, okay, which will be at what kind of coordinate? L by 2 comma L by 2, this mass, okay. Then I can place the second mass on top of this, because see, this center of mass will be here. This is block 1, let's say, okay. Then this block 2 on top of it will be at a distance L above, so its center of mass will be at L by 2 comma 3L by 2, okay. And the next block will be on the side of this, okay. So that one center of mass yeah, so that one center of mass will be here, okay, this one. So that's also having the same mass m, but its x coordinate will become 3L by 2, y coordinate will become L by 2, okay. So I'm just replacing the three blocks with their center of masses, with equivalent particles at their center of masses. Understanding now? In this diagram like this. So now I have a 3-block system. So position of the center of mass of the 3-block system is summation mx divided by summation m, and this is summation my divided by summation m, like this. Okay. So this is becoming m into, now let's take like this, L by 2, okay, plus let's take the one on top of it as the second one, so m into 3L by 2 plus m into the third one like this, so again L by 2 divided by 3m, okay. So that will become L by 2 plus 3L by 2 plus L by 2, so that will become L plus 3L by 2, so that is 5L by 6, because there's 3 in the denominator, okay. So that is the x coordinate of the center of mass. Now similarly, I'll get the y coordinate also by same method. So when I do this calculation for y coordinate also, I'll get the same thing actually. I'll get YCM also as 5L by 6 with respect to that corner. So then wherever that center of mass of that system is, it is somewhere here now, let's say. Okay. This center of mass is having coordinates XCM, YCM. So I wanted to find out this distance, PC. So that distance PC will just become square root of XCM square plus YCM square. So my final answer should become, you've done correct what you've done, but the final answer will be the distance. So 5 root 2 by 6 into LCM. Yes, Bhargav, that's correct. Okay.
yes, sir.
As you got the correct answer in terms of coordinates, you have to just convert it to a distance. Okay. So this method is always there. But my whole point is, can we make it something simpler? So let's see how we can make it simpler. Because like obviously if you get a question like this, it's comparatively easier question at JEE level. So you have to not only look at how to do the question, you have to also look at how to save time in the question. So let's come back to this diagram. So now let's go back to our idea of superposition. Like if I had a larger square of 2L by 2L, from that I have removed this mass. So this mass has been removed. Okay. Whereas the other three masses have been kept in place. Okay. Now this point is P. Okay. And this is an axis of symmetry. So I can take this only as my x-axis or something. Who's stopping me from reconverting this to my x-axis? Okay. So now see, I have, okay, let's say I've labeled these as A, B, D, and E. Okay. So for the system, A plus B plus D plus E. I'm avoiding the term C over here because I'll use that. Okay. The center of mass is over here. So these blocks, okay, the center of mass would have been at C. Okay. So now if I take these three blocks, A plus B plus D, it is a mass 3m. Okay. With its center of mass, so that is my m1 is equal to 3m. Let's say. Okay. So this green shaded portion, this whole green shaded portion, this whole thing is m1, which is 3m. Okay. And its center of mass is somewhere here. Its center of mass is somewhere here. Okay. So its center of mass is at C1, which is at some x1, which I don't know, comma 0. Okay. This is a symmetry axis. And now this part M, this is the mass M2, let's say. M2 is equal to M. So where is its center of mass located? Its center of mass is located right over here. This is where C2 is located. And C2 is at, with respect to this, what will be this? Half the diagonal. So half the diagonal will be L by root 2, comma 0. Okay. So now M1, C1 plus M, like M1 is located here, M2 is located here, but their common center of mass is where here. So I'm taking this as my origin. Okay. I'm taking this as my origin. Okay. So again, I have that. So M1 plus M2 as a system, M1 is A plus B plus D, and M2 is just the block E alone. Okay. So this as a system has center of mass at O. Okay. So M1 x1 plus M2 x2 should be equal to this thing. It should be equal to 0. Okay. So M1 was 3m into its unknown mass, unknown position x1, plus M2 was just m, but its coordinate was L by root 2. So that is equal to 0. Okay. So that is showing me now that x1 is equal to how much? It is minus L by 3 root 2. Okay. So x1 is that much. Then I can see here what is the distance PC1. PC1 will be the full diagonal, that is 2L root 2, because this is L by L, 2L by 2L. Okay, minus, oh sorry, you can say this diagonal, L root 2, not full. Okay, it is the distance PO minus x1, we can say like that. So it is my rubber. So PC1 distance, I can just write it as PO minus OC1. So it will just become L root 2 minus L by 3 root 2. So this can be written as 6 minus 1 L by 3 root 2. Okay. And if you just rationalize the denominator, that will become 5 by 6 root 2 times L. So that is PC1. And C1 is the position of the center of mass that we are looking for. Okay. So this can also be used as a convenient thing. That what is the convenience here? That I am taking this system, okay, this system of mass M1 equal to 3m, and I'm superimposing it with this M2, which is of mass M. And I know that common system center of mass is over here. So then from that I can find out that okay, M1 center of mass is on the symmetry axis somewhere over here. So I can find out where that is. Okay, so hope this method is clear to all of you.
So sir,
Yeah.
you have used that superimposition method so as to get the answer a little quick.
Yes, yes.
Okay, okay.
Only thing is that superposition method gave me the direct distance of C1 from this origin. Okay, so I still had to do a bit of calculation. I had to subtract this distance and all that. Okay, but still you can see as far as locating where the center of mass is, this is the easier method compared to making 3 particles here, then using that summation mx for x coordinate, then summation my for y coordinate. Now this is much easier. First of all, I'm locating an axis of symmetry. Then I'm using superposition, so it becomes very simple. I'm just replacing the two things I'm superposing with two particles, and their common center of mass is at that midpoint O.
Yes, sir.
Okay, so this is clear by both the methods now.
Yes, sir.
Okay. Now we will also look at one final example of moment of center of mass by integration today. Actually, there are two examples remaining, so we'll look at one of them today. So we will look at center of mass of a hollow hemispherical shell. Last time we had seen for a solid hemisphere. Okay, so we'll see a hollow hemispherical shell kind of thing. Okay. So it is like an open bowl, okay, which has a very thin crust and is hemispherical in shape. Okay. So this is a thin uniform hemispherical shell. Its mass is, let's say, capital M, and radius is capital R. Okay, so this radius over here, this is R. Okay. Now suppose I take I'm just taking this as my y-axis. Okay. Because I'm taking this point as my origin. And z-axis will be like this. So the origin is the center of the open face. So it's an open hemispherical bowl. This side is open. And the y-axis is the axis of symmetry. Okay. So obviously the center of mass will lie somewhere over here on the y-axis. So we have to find the y coordinate of the center of mass. Center of mass of this shell. We want to find YCM. So we'll use the method. In this case, we will use obviously this, but what about DM? DM will be which type of element? DM will be a surface element. It will be a sigma dA type of element. Why? Because this is a surface distribution of mass. This is a surface distribution because it's a thin shell. Okay. So its sigma will be total mass divided by total surface area, which will be 2 pi r square. Okay. Now the thing is what we should take dA as. dA should be a differential surface area element. Okay. So given the y-axis is an axis of symmetry, what should be the shape of our dA? How we should slice it? Like we had done for the solid hemisphere last time, we should slice it with a plane parallel to the exit plane. Okay. But only thing is when we slice it this time, we will not be getting discs, because it's hollow from inside. Instead, what we'll be getting? We'll be getting rings. So the differential element we'll be taking is thin rings that we will slice using a plane which is parallel to the exit plane. Is the geometry clear to all of you people?
Yes, sir.
Okay. So make a note up to here, and when you finish that, try working out yourself in the next diagram how we'll slice it into rings. Yeah, some question, beta, you were asking?
Sir, so this is aerial.
It is a surface distribution. It's an aerial or surface distribution,
Okay.
because it's a crust. Only thing is, this is how it is different than the other area distributions we had taken, like semi-disc or triangular. Those were what are called laminar areas. Laminar area means what? The area is lying on a two-dimensional plane. And this is non-laminar because it's curved into a surface. It's not lying on a two-dimensional plane. But it is still a surface distribution. It's not a volume distribution because it's a thin crust. You understood, Harsh?
Yes, sir.
Okay. So it's a surface distribution, but it's a non-laminar surface. It is not lying on a two-dimensional plane. Non-laminar means it is not on a 2D plane, but rather it is a curved surface. In 3D. Okay, so next step again we are going to slice it, but this time when we slice it, we will get rings. So we'll have to understand how to express the area of the ring, and in that an important aspect of integration will come in. Okay, so just note down up to here, then we'll take the next step. Okay, so let's understand what's the next thing I was telling you about. So when we slice it into rings now, there is an important thing in geometry of like how we apply integration that is going to be important for us here. So this is our symmetry axis, the y-axis. So what we are going to next do is at some y coordinate below, we are going to slice a ring like this, which we will get by basically using a plane parallel to the XZ plane to slice this object. So we'll be getting that looks like a ring like this. So this is a thin ring sliced by a plane parallel to the XZ plane. Okay. Now there is a matter of a sort of shortcut trick, or you can say a geometrical trick that we use in calculus, that when we are looking at the surface of a sphere and not the volume, when we are looking at surface of a sphere, we take the position of any point in terms of angular position. We don't take it in terms of the y coordinate. Okay, so let me explain further. Okay, so we will consider the important thing here to be the angular position of this ring, which is this theta. Okay. So that is a sort of convention that we'll follow when doing integration on the surface of a spherical object, okay, or even a hemispherical thing. So this is like a convention that when integrating over a surface or over a spherical surface, okay, slicing it into rings, the position of a ring is denoted by angle theta. Okay, and therefore the variable of integration that we'll use will be theta. Okay, so I'm going to demonstrate this in this integration also, how we do that. So once we take that this thing, the angular position as theta. Now you can see that this side also, this is the same theta. So what happens is the thickness of the ring. Okay, this thickness of the ring, let's write it as dl, which is the same thickness as this side. Now the ring itself subtends a very small angle d theta. This angle is d theta. See here, the thickness of the ring is like a ribbon which is wrapped around the hemisphere. So that ribbon is itself, the thickness of that ribbon is subtending a small angle d theta. So that is why the thickness of such a ring is taken as r d theta. Okay, so I'm just showing that point once again on the side over here. That is not just for the case of the hemisphere over here, but on any spherical surface. Okay, when we are slicing it into rings, the thickness of the ring is not taken as dy now. Okay, it's not taken as the vertical thickness because it's not a disk. It's like a ribbon which you have wrapped around the hemisphere at a certain position like this. So the thickness of this ribbon should not be given as dy or dx. It should be given as this curved thickness. So this curved thickness will be such that this is itself subtending a small angle d theta over here. So it's like an arc of radius r and thickness. So this arc length becomes r d theta because arc upon radius is by definition angle. Okay, so that arc length dl divided by the radius r is d theta. So that is why the thickness of a ring, okay, which was slicing from a spherical surface is always given by r d theta and not by dy or dx. Okay, so this is there. Okay, then of course the radius of this ring, okay, this is capital R, this is capital R, but that's the radius of the sphere. The radius of the ring itself is small r. So now from trigonometry of this, you can see that if this radius is r, if the radius of this ring is small r, then again it is related to the radius of the sphere because we have taken this angle as theta. Okay, this angle here is theta and this small angle is d theta. Okay, so the radius of the ring will come from the trigonometry of this triangle here, this one. Okay, so you can see that this angle is theta means here this angle is theta, or this angle is 90 minus theta. So r by capital R will become cos theta. So this has radius small r equal to capital R cos theta. So these are the two important geometrical properties of that thin ring. Okay, so I'll also make a side view diagram of this next so it becomes easier to understand, but just note down up to here first.
Sir,
Yeah, but
sir, could you just scroll up?
yeah, I'm scrolling up. Okay, done.
Yes, sir.
Okay. Yeah, so before we get into the calculation, I just want to show this geometrical thing once more to understand with clarity. So if I'm having a spherical shell like this, so you have to understand that this is hollow from inside. Okay. And these are its three mutually perpendicular diameters. Okay, so those are my x-axis, y-axis. I mean, generally I speaking, I'll take the y-axis upwards. In this case, I've taken downwards. The z-axis was going across like this. So now when I slice a thin ring, like the one we have done earlier, this is not a ring. Yeah, so when we slice a thin ring like this, so we are taking the angular position of the ring. So I'll just remove the z-axis for the moment. We are understanding the three-dimensionality anyway, so that's not a problem. So first of all, I'm taking the position of the ring in terms of the angle that this line is making with respect to my x-axis. So I'm taking the position of the ring as theta. So you can even say in a proper sign convention, the rings below have negative theta, the rings above have positive theta. Okay. And this radius is capital R. This one is capital R because that's the radius of the spherical shell. So accordingly, what about the radius of the ring? That's this one, that's small r. So you now see here, we have a right angle triangle where these two angles are theta. So that means this angle is theta, and that's how we got r by capital R was cos theta. So the radius of the ring became capital R cos theta. Okay. But more importantly, the thickness of the ring. Now the the side of the ring over here, this is subtending a small angle d theta over here. Okay. So if you look at this thin arc over here, this is the thickness of the ring. So this is subtending an angle d theta at the center, and this radius is r. So we have arc upon radius is equal to d theta. So we have the thickness of the ring is given by r d theta. Okay. So you don't need to make this whole diagram again, but it's just to explain. So, if you just isolate out that ring, that ring is like this, but the origin of our coordinate system is over here. This is the x-axis. So that's why consider this angle as theta and this thickness as r d theta. This angle is d theta. Okay, and of course this radius is small r. So this all. Okay. Now, for example, if you just want to calculate area, you can see the area of the ring. It is circumference into thickness. It's like you've taken a ribbon which was of length L equal to 2 pi r and thickness dl equal to r d theta. Okay. And this you have wrapped around into a ring like this. Okay. So it is 2 pi r cos theta into r d theta. So the area of that particular ring is given by 2 pi r square cos theta d theta. This is just the area of the ring alone. Okay. So now, for example, apart from center of mass, if I want to calculate the area, it will be integration of dA. So if I'm doing this for a hemisphere, then I should integrate 2 pi r square cos theta d theta from theta equal to 0 to theta equal to pi by 2. In this diagram, you can see theta equal to 0 is the largest ring of radius capital R, and theta equal to 90 will be the smallest ring right below over here, which will have an area tending to 0. So this will be the integrated area. Okay. Let me just yeah. So this will be the integral that will give me the area of the entire hemisphere as the integrated area. So we are taking the hemisphere as the sum of thin rings. All the thin rings going from theta equal to 0 to theta equal to pi by 2 will give me this thing. Now you can see this integration when you do it. I'll come back to center of mass, but this is just how to calculate the area of a hemisphere or a sphere, the surface area, using integration. So this is the method of doing that. So this is the integral I'm getting now from theta equal to 0 to theta equal to pi by 2. Now you know the antiderivative of cos theta is sine theta. So you'll simply get 2 pi r square into sine theta, limits from theta equal to 0 to theta equal to pi by 2. So upper limit is sine pi by 2, which is 1. And lower limit will be sine 0, which is 0. This is 1 minus 0. So as expected, the area of the hemisphere is 2 pi r square. Or if we were doing for the full sphere, we would have taken theta from minus pi by 2 to plus pi by 2. Or we'd just calculate the area of the hemisphere and double it. So this is how to calculate area, or rather surface area of hemisphere by integration. Okay. So just make a brief note of this part. Okay. So this is our differential area element. Okay.
R.
Yes,
Sir, how the upper limit became pi by 2?
I'll explain. Okay. This is a differential area element, which is a thin ring, which has an area of this much. Okay. How it became? Okay, let's see. So I'm just doing this integration for the hemisphere. No? So the hemisphere is like this. Okay. Now in the hemisphere, any general ring is over here, where this angle is theta. Okay. So for the uppermost ring which I have over here, what will be the angle? It will be 0, that you can see, right?
Yes.
इस वाले के लिए theta 0 होगा. But what about the lowermost ring right at the bottom, जो यहाँ पे है? For this ring, which is almost actually a dot, this last ring, for this theta is how much? 90.
Yes, sir.
So that's how it's going from 0 to 90. Bhargav, I'm just going through your doubt in a moment. Just a moment. Is the doubt related to this thing, the image you have sent, Bhargav, or is it related to this diagram that I have made?
So the diagram, is that actually like that in case if I consider in that real life situation, like what I have shown in that picture?
Okay, I'm just going through it. I'm just. Just a minute. Okay, Bhargav, unfortunately, I'm having some problem opening that file. Can you resend it once? I think where I've downloaded it is got corrupted.
Okay, sir.
Or you can just send it to me on WhatsApp also. Like you can take an image on WhatsApp and just, you can take an image in your phone if you have send that also. Yeah, I've got your message. I'm going through that. Yes, Bhargav, what you've done is correct. The compass that you put against the bowl, no? So if you use that compass, and you take it completely around that bowl, you will be tracing a ring. Your pencil will trace one circle, and the pointer's end will trace another circle.
Yes,
Right,
sir.
Bhargav? So those two circles between them, no, they are very close to each other. So between them, those two circles will slice a thin ring. And the thickness of that ring only, which is the distance which you correctly said, is the distance between the pen and rather the pencil tip and the pointer. that distance is only your DL, which is RD theta.
Okay, so like my interpretation was correct in that real life example.
Yes, correct.
Okay.
It is correct. Okay. So I'll just try to illustrate to everyone here what we are talking about. Okay. So basically what Bhargav has done, he's done something very interesting actually. He's tried to make a live demonstration of it. Okay, if he had video available, I mean, if he had more time and he could make a video and all that, he could have actually made a video demonstration of what he's doing. So he's actually taken a utensil, like a, like a bowl that you eat in, as a bowl pay. Now he has put a compass. So the compass, like I'm showing it like a divider because it will take me more time to draw and all that. So let's say this is a divider. So it has one pinpoint here and it has that, thing like this. So he's opened the divider slightly and placed it somewhere over here. So the two pins of the divider are touching the inner surface of the bowl at these 2 points, let's say A and B. So the distance between these 2 points A and B is our DL. Okay. So now see here, while this is happening, if I join the center of the, the open surface with the points A and the point B, both the points A and B from this center will be equidistant. They'll be R. Okay. And this angle is d theta. So now you can understand why the distance AB, which is DL, is equal to R d theta. Right, Bhargav?
Yes, sir. But like that, the points where that metallic bars are meeting, that is considered as the center of that spherical area. That
the two metallic bars. Acha, you can place this over here also. But it's
yes,
a little
sir.
difficult to do. If you do that, then even nicer. Then though your two prongs of the divider only, they are only becoming R.
Yes, sir. That is what I was showing.
Okay, but now see, if you want to trace the circle, what you'll have to do is you'll have to hold this steady so that A and B are in the same horizontal plane as you're tracing it. So A will trace a circle like this and B will trace a circle like this. And because A and B are very close to each other, so you'll get that thin ring that you're tracing. So that ring will now have that property that its radius small r will be equal to capital R cos theta. If I've taken this angle as theta, I take this angle as theta, which is the same as this angle here. So you have this, okay, and the thickness is r d theta. So the area of that ring is 2 pi r square cos theta d theta. That's all right. So I think this is now pretty clear to all of us, right? How we are slicing the rings and all.
Yes, sir.
Okay, so now let's come back to our problem of center of mass. Okay, so I'll go back to our original diagram here. Now in this original diagram, you can see that now I know the area of this ring. I've just learned how to express that. That is 2 times pi into small r into dl. So that is becoming this thing. So let's come back to our center of mass problem. Center of mass of hemisphere. Okay. So in this now, see this ring that we've taken. It has an area dA which I've already written 2 pi r into dl, which I have shown as 2 pi capital R square cos theta d theta. Okay, this thing. So what about its mass? Its mass will be sigma dA. Now sigma we had seen earlier was the total mass of the hemisphere divided by its surface area, which was 2 pi r square. Okay, so its mass dm is becoming something very simple actually. It is just m cos theta d theta. Okay. So because d theta is a very small angle, the mass is also very small. So dm is this thing. Dm is m cos theta d theta. Okay. Now I can what is the y coordinate of this thing? It is this one. This is the y coordinate. So this dm is located at y equal to, now see in my diagram, what will that y be? It will be r sine theta. Is that correct? Right, this is correct now?
Yes, sir.
This distance is y, this distance is capital R, and this distance is small r. Okay, and this angle is theta now. So this angle was theta. Okay, so y is becoming capital R sine theta. So now what I have to do for center of mass, I have to calculate YCM of the hemispherical shell. So that will be integration YDM divided by total mass. Okay, so that will be integration of y को replace कर दो with r sin theta और dm को replace कर दो with m cos theta d theta. And we are all taking all the rings again in my diagram from the top one, which is at theta equal to 0, and this is the largest ring of radius capital R, to the lowest one, which is at theta pi by 2, and its radius is almost tending to 0. So now you can see, take the constants outside m into r. So this becomes a very simple integration, sin theta cos theta d theta from theta equal to 0 to theta equal to pi by 2. And of course, I have to divide this by m, so m will cancel out. So dimensionally, this will have the dimension of length only, which is the radius. So I'll get some factor into radius. So I just want you to note this down and try and do the integration yourself. Okay, I'll give you a hint how to do the integration. There are two things. One is you can use the formula of sine 2 theta. No, you must have learned sine 2 theta is 2 sine theta cos theta. वैसे भी कर सकते हो. Or you can use substitution also, because you know cos theta is the differentiation of sine theta. So you can use substitution also. Both the methods are equally easy. Okay, anyone done the integration? So I'm just minimizing a bit while you note this down. So one more step, I'll cancel the m's, and I have this r into sine theta cos theta d theta from theta equal to 0 to theta equal to pi by 2. So for doing this integration, I have two methods. Okay. I'll show those methods here. One method is integration sine theta cos theta can be expressed as integration of sine 2 theta by 2. Okay, so that is half into integration of sine 2 theta, and that will become half into minus cos 2 theta by 2, okay, plus c. So that's one thing we can do. Okay, so one way of solving this integral, the indefinite integral will be minus 1 by 4 cos 2 theta plus c. And then you put the limits 0 to pi by 2. Another thing we can do on the other hand is that we can put sine theta as z, suppose, substitution. So cos theta d theta, but with a becomes dz. So the integral becomes z dz, which is z square by 2 plus c. Okay. So seemingly it's a different answer we are getting. Okay, we'll get sine square theta by 2 plus c. But you can always express cos 2 theta in terms of sine square theta. No? So you'll see that they are actually equivalent. So that is something interesting about integration also, which I'll show you through this. So I'm just doing the indefinite integration here. Of course, we have to put the limits where we are actually doing the question. So when we put the limits and all, so it might look like two different methods are giving us two different answers, but actually that's not the case. The answers are equivalent because I can always write cos 2 theta as 1 minus 2 sine square theta. Okay. So if I can do that, I can write this as minus of 1 minus 2 sine square theta by 4 plus c. Okay, and that will give me the same thing actually. So that will give me sine square theta by 2 minus 1 by 4 plus c. So that 1 by 4 is absorbed in the constant only. This is constant. Okay, so it is basically sine square theta by 2 plus c. So this and this are the same. So there's something interesting about the integration here also. So next step when you're doing, you can write YCM as R into, you can either write it in terms of this integral, it would be minus 1 by 4 cos 2 theta, raising it from the limits 0 to pi by 2, or you can also express the integral as this one, which is sine square theta by 2, and raising the limits from theta equal to 0 to theta equal to pi by 2. And whichever of the two forms of the final answer, whichever of the two forms you substitute the limits, the answer will come out to be the same. And in fact, the answer will come out to be r by 2. So interestingly, a hemispherical shell has its center of mass right at the midpoint of that symmetry axis, between the circumference and the center of the face, or the center of curvature. It's right at the midpoint. So there are lots of little different steps involved over here. Please let me know if something is not clear.
Sir,
Yeah,
so sir, the final answer R by 2?
yes, the final answer is r by 2. Deep, you check your answer, you should be getting r by 2 and not r, no? Same.
Yes, sir, I
Pradnesh.
made a
So
mistake. I skipped
okay.
1, 2.
1, 2, no? Okay. Pradnesh, you also check, no? Right. So this final thing, as I said, whether you substitute in this one or that one, this one is a little bit more complicated. You will have cos of 2 times pi by 2, so that's cos pi, but with a minus sign divided by 4, and then minus of cos 0 divided by, or minus of minus cos 0 divided by 4. Okay. So this is the upper limit, this is the lower limit. So let me actually write this in more systematic manner. If I'm using this one, I'll have like this. The upper limit will be minus 1 by 4 cos of pi. Okay. And the lower limit will be minus of 1 by 4 cos of 0. Okay. So cos pi, you know, is minus 1. So it's like you have to be very careful with the steps. And cos 0 is 1. So that's how we get r into 1 by 4 plus 1 by 4, or r by 2. It's a long and arduous route, but you come to the answer. Okay. Whereas this one is somewhat simpler actually. To substitute in this, you just have r sine square pi by 2, which you know is 1, minus sine square 0, which we know is 0. So directly we have, sorry, not by 0, by 2. That would be a huge disaster if we had 0 in the denominator. Okay. So r by 2. So end of the day, what it means is that the hemispherical shell, its center of mass is right at the midpoint of this vertical radius. If this point is O, so the center of mass is just at r by 2. Okay, so this is another one of the standard examples of center of mass that you have to remember. Okay, so I was telling you last time that I'll give you a list of all the values of center of mass that you should remember. So let me give you that list before we end up today. So standard formulae for center of mass.
Sir, you are not sending PDF.
I'll send, no?
Okay, okay, sir.
So in just your notes, it will be there. Okay, which standard formula you have to remember. Okay, of course you will find most of these formulae in any standard book also. It's there in your they're listed out in your module also, but just for your reference here. So you should remember for semi ring, okay, then ring of, sorry, thin arc of arbitrary angle. Okay, so these are all examples that we have done in class. Okay, arc, of thin rod bent into an arc. Then semi-disc, then solid cone, then solid hemisphere. And the last one we did today, hollow hemispherical shell. Okay. And one more which you try yourself, and we'll discuss in the next class, hollow open cone. Okay. We have done the solid cone. Now just imagine that this is hollow from inside, and it's just a shell which is in the cone shape, just like we had the hemisphere today. So this side is open, and this is a thin uniform conical shell. You know the center of mass of all these. So that, you know, in the exam, if you have a problem related to any of these, you don't have to sit and derive it. For example, if in the exam you have a problem where you have to actually find the center of mass of a circular arc, which is suppose obtaining an angle of 60 degrees at the center. So you know that the center of mass will lie somewhere over here, where if the radius of this one is this, okay, then first of all it will lie on the angular bisector, 30 degrees, and that distance OC will be how much? R sine alpha by 2 divided by alpha by 2. So here alpha will be how much? 60 degrees or pi by 3. So OC will be R sine pi by 6 divided by pi by 6. So that will be 6R into half divided by pi, or 3R by pi. So this is all the time it should take. It should not take more than this much time to work out where the center of mass of this thin arc is. This is example 2 from here. So that competence you have to have, you know. Okay, people. So with that, we will conclude today's session. Now I'll be sending the PDF and the recording of this lecture by tomorrow itself. And along with that, I will send you a list of questions to do from HC Verma in your module, which are application of position of center of mass and basic application of momentum conservation kind of thing, like we had seen last time. Last lecture, we had seen one example of momentum conservation. So those type of problems. And now we are done with the center of mass part. So next lecture onwards, we'll fully concentrate on that momentum conservation and linear momentum. And eventually we'll come to the very important part of collisions. So we are coming to an extremely important part of your mechanics. Okay. So before we get into all those type of problems next week, please, complete problems related to basic things like position of center of mass and motion of center of mass, basically the homework problems that I'll be sending. And if there's any backlog from work energy or anything before that, make sure that you're doing that also, because next week onwards you will have to really concentrate on momentum conservation and collision type of problems, which is like at the core of mechanics, very important part for us. Okay, so that's it for today's session, people. Wish you all the best.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Okay, bye, people.